Hello, everybody. Welcome to Science Streams and our Wednesday night connected conversations, where tonight we have a returning guest, Professor Matt Bellis from Siena College. He is a particle physicist and he studies baryon resonances using data from CLS experiments at Jefferson Lab in Virginia. And he's in the search of new physics. And I know he's also a great professor at Siena, an advocate for his students and research, and really wants to know the unknown about the universe and dark matter in particular. Welcome, Matt.
Thanks very much, Scott. Thanks for having me here.
Anything else new that I missed in like my little bio of you that you wanted to share?
So interesting. So my current research these days. The baryon resonance researches that was my PhD work. That was at Jefferson Lab in Virginia. And these days, my main research is with the CMS experiment, which is one of the experiments at the Large Hadron Collider. This is in CERN, which is a particle physics lab in Europe. It straddles the border between France and Switzerland. So my physics interests have moved around the world, but it's been fun. It's afforded me and the students a lot of interesting opportunities.
No travel opportunities in the last year.
Not in the last year. We ran a workshop last year at Fermilab, but of course it was virtual. And this year we're doing the second iteration of a workshop. This is a workshop designed to take real open data from the CMS experiment at the LHC and make it analyzable and available to theorists and honestly anybody in the public who would want to like analyze the real data. We ran the first workshop of its kind last October, again virtually. As you said, it was going to be at Fermilab in Chicagoland, and we were all ready. And then obviously everything had to be moved to remote. We hoped we would be able to do stuff in person at CERN this summer, and we are in the process of working on it remote. But at least it'll keep the momentum going with teaching people how to access and analyze these data.
Yeah, in case people don't know, a lot of science now is just done through data sets. Whether it's from CERN or you get your atmospheric data from NOAA or NASA. I had an oceanographer on a couple of months ago who had never been to the ocean, but he just processed the temperature data from the ocean. So he was an oceanographer.
That's right.
So it's one of those weird things how science has really changed, especially in the last 25 years with big data.
Yeah, and I would, I want to give a shout out. There's at the root level of all of this stuff, somebody is taking the data.
Yes.
Right.
Yep.
Somebody's going out on the ocean.
Yep.
Tens of thousands of people built these experiments, and thousands of people run these experiments. But to your point, the way to share the data so that more people have access to it and more people can analyze it, you're absolutely right. It's no pun intended. It's been a sea change in how people really get to like analyze and make new discoveries with this data that's been made available through the hard work of others.
Yeah. Now the data you're talking about, I find it interesting because you are taking that classic equation, E equals mc squared, and using that to look at the energies and the masses of these particles. Am I correct?
That's exactly right. So that's exactly right. And I tell the students this, that like, whenever I sit down to do analysis, like 80% of my time is like writing out that equation. And, this is a science, stream, so I can be a little bit more precise, right? E equals mc squared is for a particle or anything sitting at rest. And in our experiments, it's moving very fast. And so we have E squared equals mc squared squared plus the momentum squared. So you add the momentum squared. And in our experiments, what we do is we measure the energy, and then independently we measure the momentum. And then from that, you can infer the mass of these particles. And as you mentioned earlier, you're looking for signs of new physics. You're looking for new particles with new masses.
I'd also like to add that it also seems complicated, but it's nothing that high school, level, upper level math couldn't handle, right?
That's
It's
exactly
it's
right.
algebra, and then you might write a program to run it for you, and yeah,
We have simplified versions of this data. I host a website called Particle Physics Playground, where I've
hmm
taken data from the CMS experiments as well as other experiments and make it available in a simplified format with relatively simple Python. So if someone has started learning the Python programming language, and it is on the level of you have to take a number and you square it and you add it to another number that's squared, or you add three
hmm
numbers and you square them. Like, it is that level of like algebra. Like, it is embarrassingly simple, the math that I tend to really use on a regular basis. The programming can get a bit more complicated. Um, and there's a few other factors that get involved. But honestly, when we're using special relativity, we're doing a lot of our
hmm
analysis. It really is like adding and squaring numbers and taking the square root. And that's about it.
Yeah, and it's amazing how simple. I mean, there is a complexity to it. You're just not going to sit down on an afternoon and be like, yeah, I'm going
Sure.
to do this
Sure, sure,
on a
sure.
lark.
Sure, sure, sure. But
Unless you're a real nerd, then you probably could. If you're like, you already got the chops and you're kind of like, all right, but if, meaning like you already know how to use GitHub or, and these other
right, right,
things,
right.
you can jump in a little bit easier than if you're, a high school student right now looking at doing it. It could take you a while, but, there are resources out there to help you. You do have some tutorial videos. I just
That's
found them
right.
online.
Yeah, that's right. So a couple summers ago, I had some students put together some, like you said, tutorial videos to kind of really get people jumped in as early as possible. We moved everything to Google's Colab environment, which
hmm
means that you can start running stuff in the browser. You don't even need GitHub
Ooh,
if you don't want to. So
okay.
like, you fire up, any of the tutorials, and in your browser, you can download subsets of the data. You can run it. There's tutorials about how to like piece together data. Again, not just from CMS, from the Clio experiment, which ran at Cornell for a number of years, from the Babar experiment, which ran out at SLAC at Stanford out in California. And then we just uploaded some data. We need to clean it up a bit. As a proof of principle, we showed that you can visualize data from the IceCube experiment, which is a neutrino experiment in Antarctica, where
hmm
they melt these holes about a kilometer down into the ice, and they lower down on these wires these very, very sensitive photosensors that measures light. And they basically put a whole bunch of these holes in the ground, and they basically instrument like a square kilometer. And so deep under the ice, when particles come through, high energy neutrinos from outer space, they cause these little showers of particles, which create light, under the ice in the pitch darkness. And you can see these flashes of light. And they had released some open data as well, which we also put up on the Particle Physics Playground.
Now, I want to ask, there's experiments like that, and part of it is trying to find dark matter, correct?
Right. So the IceCube experiment was not initially intended for dark matter. However,
hmm
like many things these days, we are trying to use everything at our disposal to explore every bit of the possibilities that could be out there for dark matter. Yeah,
Because you keep coming up empty.
because we keep coming up empty. We have seen no definitive evidence for dark matter. There's a couple of interesting hints. There was a recent announcement in the last year by an experiment called the Xenon Experiment that sees the language is called an excess of events in a region where they did not expect there to be.
Is
And
that
then
the
there's
one they're trying to replicate it? Like someplace, of course, you're trying to replicate everything, but you
No,
know,
I think you might be referring to, there's the Dhamma Experiment, which for like 13 years has claimed we see dark matter. We totally see
mhm.
it, and nobody else does. And other people have actually replicated their experiment, like building almost the exact thing. and have not seen it. No, this is a relatively new one. It's a well-established experiment. It's the Xenon Experiment, which is a liquid xenon detector underground, and they see at very low energies more interactions in their detector than they expected.
Right.
And I say it using that language of more than they expected, because one interpretation could be, hey, it's dark matter. And the other thing is it could be some really subtle experimental effects that they just, are still understanding that they had not taken into account.
Right. I think one of the most amazing things in physics, especially, is the level of sensitivity of the instruments.
Yes.
How many decimal places it goes out to, and how that is even possible. I mean, does it boggle your mind? I mean, when you think about it, and you're just kind of like, what? Really? That many decimal places?
No, absolutely, absolutely, right? So most of my research these days focuses at like the Large Hadron Collider. It's the highest energy particle collider, mankind has put together. But for a number of years, I was working, analyzing some open data from a dark matter experiment called the Cogent experiment, and I worked with some of the scientists on it at University of Chicago. And this is an experiment, right? So I work on these giant colliders, huge radiation everywhere, and the radiation damages everything, and you got to replace it after a few years. And this like sat in a mine for 4 years. And it was so quiet radiation wise that when this thing is on the surface, right? So it's a germanium crystal. And when it sits on the surface, it is constantly bombarded by cosmic rays, which changes some of the germanium to different isotopes. So this is similar to carbon-14, right? Cosmic rays hit nitrogen in the air. It forms carbon-14. The carbon-14 decays away over long periods of time. Well, some of the isotopes that are created in this germanium crystal have lifetimes on the order of like 60 days or 270 days. And so in this 4-year data set, you see these like background radioactive decays, and we're talking about like 1 decay a day or so. But after a year, it's like even quieter. It's even less radioactive. And after 2 years, there's even less data. There's even less background, sorry. And you're at the level. So this is crazy to me. You're at the level where some of the background is coming from the electronics, because the resistors have very, very, very small trace amounts of like thorium and plutonium in them. And then the Teflon tape. So Teflon is CF4, and the carbon has small traces of carbon-14. So just like the Teflon tape is like a source of like background radiation to these experiments. And it's crazy, like the sensitivity, as you say, that they're getting back to, and the things they have to take into account for these experiments that like in my day job physics experiment, I generally don't have to worry about.
Right. And I think that's where that whole body of knowledge comes in, right? You go back to the first people that tried doing it. How did they fix it? Right. And then someone else comes along and they're like, well, we did it and you didn't account for this, but we fixed it this way. And then the next person comes along. You know what? You didn't do this to account for it. And, you get where you are by standing on the shoulders of giants, and, everyone benefits from, past people's ability to refine their methods and get better and better. That's why you have those seminal papers, I would assume.
That's right. That's exact.
They show you how to do it.
We're all building off of each other. We're all building off of each other. Yeah.
So
yeah, there's this one experiment that one of these other dark matter experiments, they have to shield their experiment using lead. And the lead that they get is from Spanish galleons that sank 400 years ago. And because this lead was processed 400 years ago, and then underwater where it was shielded from cosmic rays, it is less radioactive than many other lead bricks that you would use for these experiments. You talk about going back and like standing on the shoulders of giants. This is just like, 400 years ago, people processed this lead, and it actually helps me like nowadays for entirely different reasons.
That's great.
Yeah.
And it's kind of daunting. It's also, I think, a juxtaposition, like you said, in those experiments. You talked about that that one like germanium crystal, that one little box versus an entire like CERN.
I know.
And it's and I at one point, they had said, as I'm reading, in just a general like literature here, not in scientific literature, that like the age of these small colliders was going to be over because they have these huge, colliders. There's that
Right.
talk for a little while.
Right.
But then, as you know, Fermilab is still putting out,
Yeah.
great science. I
Great sign.
don't see them going anywhere. Any comments on that?
Yeah. So right. So there's two jumping off points I could take from what you said. So let me say one thing um in defense of future small
Hmm.
experiments, right? So with the LHC, the Large Hadron Collider, it's a 17-mile ring. There's talk about the next generation, which is going to be 50 miles around, right? So who knows if that's going to happen. There's there's in parallel an incredible amount of work, however, trying to shrink the size of these accelerators. And there's been talk about like being able to take that 50-kilometer ring and turn it into like a half a kilometer, if they can get this new technology. This is called Wakefield Acceleration. Um, and that would be amazing if you could get to the same energies with a much smaller detector, or sorry, much smaller accelerator, right? So the idea is this new technology might be able to accelerate protons and electrons up to the same speeds now, but in like a tenth of the size, which, then you could build something and not have to build a 50-kilometer ring. The other thing that, however, is like you said, these smaller colliders that aren't going anywhere, right? So there's Fermilab, which, as you said, is smaller than the LHC. There's an experiment in Japan, Super Bell, which is also a small experiment. And both Fermilab and then these other experiments, what they are trying to do is instead of going to very, very high energies, they are going to what's called the precision frontier. And this goes to your statement
Right.
earlier about going out to like 20 decimal places. Is that if you can basically run some of these measurements long enough, you collect enough data, and you have new electronics than you did 20 years ago, you've improved your equipment, you're able to reduce your error bars such that you're making precision measurements that you are effectively probing whether or not particles exist at high energy. So these particles might exist at higher energies than the LHC can reach, but they can still influence lower
Hmm.
energy interactions. The only way you would see those is with an incredible amount of data. And this is where Fermilab and some of the other experiments really have, they've carved out their niche now at this precision frontier.
Right. I would think it would be also easier to replicate studies in that
Yes.
way as well. Yeah, I
Yes.
mean,
Yeah.
like,
Yeah.
how do you replicate CERN's, the LHC? Do you build another one? I mean, you know, it,
The closest thing you do is you have one LHC, but you have like there's like two experiments, CMS and Atlas,
right.
that they both have slightly different
Okay.
technology, but they're basically doing the same thing. They both announced the discovery of the Higgs. So you use the same accelerator, but you have different experiments. Now there's a question about, with the next big collider, the experiments are going to be even bigger. Can you afford to have two experiments? Even though, the checks and balances has been very good, the friendly competition has been very good, but maybe at some point, just financially, it doesn't make sense for the world to have two large experiments like that.
Hmm. I also think of experiments like LIGO, where they
Right.
did build multiple of them and they want to build more of them. And
Yes.
that
Yeah,
is a
yeah, yeah.
great example of, detecting the same thing in many places and verifying results that way.
That's right. And you need more than one LIGO to get the direction, right? You
Right.
need like LIGO and then Virgo, which is in
Hmm.
Europe. And the more you have, the more like directionality. I have made a half joke, half serious. I'm a little bit of a Keynesian economist. This was Keynes who said, if you want to stimulate the economy, you pay people to dig a hole, and then you pay them to fill the same hole back up. That the government puts money into the economy by just like, you know, if the US wanted to get out of, a recession, we just decide to build 10 LHCs in the United States. We build 10 of them. We all have competition. We'll have the SEC, in the conference for the LHC, and you'll just employ tens of thousands of people. Everybody will be competing to discover the Higgs, the next. Everybody will be, you'll employ tons of people. But I know that's a bit of a pipe dream, and we're probably not going to have a dozen LHCs in the United States, but one can dream.
Would you have enough expertise to build and run that many?
This not at first, and then you would start
Right.
training the next generation of, how do you, all the engineering that goes, I've visited CERN, fewer times than I would like, but every time I go, I am so amazed by, it's not just the physicists, right? It's the engineers and the infrastructure and everything that goes into making these facilities work. It's similar. My wife does work sometimes at Argonne National Labs, which is a national lab facility just outside Chicago. It employs like 6,000 people. They do work not just on, particle physics, but on battery design. And they've got this massive X-ray, synchrotron light source. There's just so much energy and so many ideas going on that, maybe you couldn't populate 10 LHCs in the US, but I bet you would have a whole generation coming up that's like, oh, I want to go work in like the Midwest LHC versus like the Southwest LHC or
Right.
something like that.
Hey, Uncle Bill, welcome. And please, any questions you have for Dr. Matt Bellis, please get them out. And speaking of like that, having enough people, that's where like education comes in, I think,
That's right.
and the lack of, engineers that we see or expertise in certain areas. And I like the idea of having more people involved in more places. I mean, if you have more people growing up, be like, yeah, my dad's an engineer, more people become engineers. The more people
That's
that
right.
are physicists, I mean, because you end up being what your parents are often.
Yeah.
My kids
Yeah.
are already becoming teachers.
Right.
I don't know. It's funny how that is, but because even if you don't end up in the same career track, you have an appreciation for what your parents did, or whoever your caregivers were, how you grew up. And often that's even like uncles or grandparents and things like that. And the more people that have that's why we're here. More people that have an appreciation for science and what happens, the better.
Or that's right. Or what you see in your community, or it's like not even at home. Like my 7-year-old son, my wife is a physics professor at, Union College. I'm a physics professor. My son is already like, there's no way I'm being a scientist. He's like, no way. He says that now, and maybe he will. But like, I think it's what you see in the community, right? Like, so I grew up in Jupiter, Florida, and there was a large Pratt and Whitney who make airplane engines plant. And I think a lot of kids saw that as, their parents worked there or friends of their parents worked there as an engineers. And they saw that as something like, oh, that's what people in my community do. And when I worked at Jefferson Lab, at times down in Norfolk, Virginia, we would host these open lab days where you would have people from all over like Southern Virginia come and tour the lab and see the accelerator. And it's the same thing at Fermilab. There is a palpable awareness in the Chicagoland area of Fermilab. And I think there are so many kids that at some point they go on a field trip to Fermilab. And this is where the top quark was discovered. And it's this beautiful, massive 15-story building. And they get this idea that this is what people in my community can aspire to, whether it's an engineer or a scientist. And I wish every state had a national lab that was driving distance. Like New York State has Brookhaven National Lab.
Yep.
But it's, it's a 4-hour drive down there. Everybody should have a national lab within 2 hours. That's my pitch if I ever run for politics, which I won't.
Yeah. We do locally have the the atomic lab in Schenectady.
That's true. Yeah, that's right.
So
that's right. Knowles.
You can't get into Knowles. I mean, it's blocked off, but
that's the thing, right? That's the thing, right? It's totally
but it's there.
Yeah. That's right.
And I mean, there is something to be said for like, I go back to the engineering again with GE. I mean, they still there's a lot of facilities here that do make
Yes.
giant generators and engines and
I used to work there.
blades. Yeah.
Yeah, I used to work at General Electric in Schenectady before I went back for grad school. And those buildings, and I saw some of them being assembled. And like you said, the rotors, the blades, these like 20 feet across, and like these just the building itself was like the biggest building I've ever been in. And it is, that's years and years of people learning how to scale things up, and how to have a
Hmm.
lathe that can handle like a 20-ton rotor. It's incredible. It's absolutely amazing engineering. And with you were talking about experiments in Fermilab. There was these recent results that came out from this G-2 measurement.
Hmm.
And that was, you talk about Brookhaven. That was an experiment that was at Brookhaven in New York. They floated it down, the Atlantic up the Mississippi. And then they drove it to Fermilab, where it had a second life and a second experiment. And that was something that was like driving through communities, like at 2 miles an hour, or something on the road. And people came out to see this like giant scientific, 50-foot,
How
iron.
often does that happen?
Exactly, right?
I didn't even know
Somewhere.
it occurred until I read up on it. I saw the release and I'm like, all right, let me read this. And I'm like, what? I'm like, so to
Right.
replicate the study, they moved the entire apparatus.
Yes. Yes. Yes.
It-
Yes.
it-
From
uh,
yes.
from
So for
Brook.
people that may not be aware of this, there's an experiment that ran in the late 90s, early 2000s at Brookhaven. It was called the G-2 experiment because they were measuring a property of a subatomic particle called the muon. It's a cousin of the electron. The property is called G-2, and it's related to basically how much it acts like a magnet. And this experiment ran for a number of years at Brookhaven, and then the funding ran out, and they said, look, we can't really do much more with this, with the infrastructure at Brookhaven. And the people at Fermilab were like, haha, if you could get it to us, we could run this. And the people were like, okay, that's nice, but this like 50-foot iron ring can't really be disassembled. And then someone, and I would love to know like who it was that was like, you know what? If we put it on a barge, we could float it down the entire US coast, around Florida, into the Gulf of Mexico, up the Mississippi, and then at some point they put it on like a slow truck and drive it from Iowa to just outside of Chicago. And I remember, because I'm, particle physics, we're all, you kind of know what's going on in the field. This is not my experiment. I want to be
Right.
clear. I am taking no credit for like the amazing people that made this measurement. This is all credit to them. But you're aware of what's happening. And I was actually visiting my parents in Virginia when they were moving this. And I remember like it was on a barge. This is like tens of millions of dollars. They're basically saving money. They talk a lot about this as like recycling equipment. This is green physics. We're recycling an old experiment. And there were storms that were coming in, on the Atlantic. And so every now and then the barge would have to come into port to like avoid a storm. And then, it was actually around Newport News in Virginia when I was down there. And then it would like go back out to sea. And somehow, and then they got it to Fermilab, and they kind of like got it hooked up and were able to inject muons. And then just a week or two ago, they announced these results that could be like really, really profound. They could be the first hints of new physics that we've really seen in like, a couple of decades or so.
Of course, they hype it up. The standard model is broken. Right. Right.
So that is what some of the press releases are. And you are correct in that there was some hype about it. So if you want, do you think now is a reasonable time for me to talk
Well,
about
we've already
it?
transitioned, so we
Okay.
might as
Okay.
well. I mean,
You're good
we'll
point. Good point. So this experiment was designed to measure again this muon, which only lives for about 10 to the negative 6 seconds. How much it acts like a magnet. So this thing exists for on the order of microseconds. The question is, how much does it act like a magnet? And so you put it in this giant ring, and the magnetic you get it aligned so that its magnetic field causes it to precess around the ring. And then when it decays, it emits an electron or a positron, and you detect that particle and you know which way its magnetic field was pointing. And they ran this for a year, and they're going to be running it more, but they got the first set of data out. And what they're looking for is to measure a number incredibly precisely. So the result from this whole experiment is a number. And this number should be 2 if there was no quantum mechanics. But because of quantum mechanics and quantum field theory, it's just a little bit off. So they say if you subtract 2 from it, you get all these numbers out to so many decimal places. They ran the experiment blind. And what that means is there is a clock that they use to time everything. And that clock has a value associated with it that was, I think, randomized effectively. And there were 2 people at Fermilab that knew this magic random number to subtract. And these 2 people had the number written on an envelope locked in a cabinet at Fermilab so that no one could accidentally know what the answer is and maybe subconsciously bias the analysis. Because if you started, if you were doing some
Right.
preliminary work, you'd be like, oh, that's interesting. Let me keep doing that. And it's like, no, 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 no. You want to be agnostic while you're doing this.
Mhm.
So there were 2 people that this number was locked away, and only like 2 people had the key. And when they made the announcement, I watched the webinar. They had actually done a Zoom recording of the few hundred people in the collaboration. They got the number. They entered it into a Jupyter Python notebook, like in real time, and like instantly they were able to run it, and it quickly does the analysis, does the fit to the data, gets the number out. And so they put the number in, and then in real time you've got like a few hundred people on Zoom going like, oh my gosh, that's amazing. And they actually recorded it and they played it for everybody when they made the public announcements. So to your point about like, is this hype? Is the standard model broken? We have an incredible theory that allows us to predict what this number should be. But the theory is very, very hard to do the calculations. And that's not just because when I say it's hard, there's just a lot of calculations you have to do. Some of those calculations rely on numbers taken from experiment. And I'll come back to why that's significant in a second. So they've got a number from theory, they've got a number from experiment, and you've got error bars on each of these. And when Brookhaven ran their experiment at first, the theory error bars were big enough that it was hard to say whether or not they really saw something. But over the last 20 years, the error bars on the theory have shrunk. And then the question was, when they ran this at Fermilab, would they be consistent with what had been taken at Brookhaven? They were consistent with what had taken at Brookhaven, and now there's this big difference between theory and experiment. The fact that these 2 numbers are different does not tell you exactly what it is. And I'll explain that in a moment again. Now, to your question about like, does this mean definitively that there's new physics? I think most particle physicists say, we've got to be careful. There's still a lot of checks to catch. The people who did this experiment, I think, did an incredible measurement, and I think that their number is valid and real. But when I mentioned that there's this theory that makes these predictions, and they take some of their numbers from data, there is a complementary way to do the calculations, and it is called Lattice Qcd. And in that, you do not take stuff from data. You really do everything from first principles, but it is incredibly computationally intensive. Like you have to run your computers for months to make the calculation. And the lattice theory prediction is much closer to experiment than the other theory. And if you only knew about the lattice calculations, you might not be so enthusiastic about new physics. Now, The lattice people say they still have a lot of checks to do. The experiment people say they have a lot of checks to do. So I think everybody's kind of like cautiously excited. This is like,
Hmm.
we're going to learn something. We're going to learn that the old theory maybe wasn't quite right, or we're going to learn something new about, this experiment and how it's made. Um, but even if it is true that the theory and the experiment really, really, really don't exist, it doesn't tell us what the new physics is.
Hmm.
And there was a lot of jokes being made that, like, once this announcement got made, there was like, 100 new theory papers out the next day from all the theorists with their, like, their pet
Hmm.
models trying to explain this one number. But this number does not definitively point to what the new physics is. Maybe it's dark matter, maybe it is a new force of nature. Um, it doesn't tell us exactly what it is.
Yep.
And I was trying to like come up with a good analogy for this. And the one that sticks in my head was in the 1700s, there was this, I think his name was Schleichorn. I should have looked it up earlier, but he was trying to measure the
Hmm.
mass of a mountain using gravity. And he had this ball, this little pendulum. I mean, it wasn't swinging, but he had this little ball, and he brought it near a large mountain, and the gravitational pull from the mountain, pulled the
Right.
pendulum toward, and from it he was able to measure, effectively, I think, like the mass of the earth, the mass of the mountain. Anyways, long story short, very quickly from all of this information, you find out that the earth does not does not have an average density of granite, right? On the surface of the
Yep.
earth, everything's a rock. And the earth is heavier than if the earth was just rock, and it has a greater average density than if it was just rock. Now, you and I know, because we learned in elementary school, that there's an iron core, that there's iron. But if all you know is that the density of the earth is not rock, it doesn't tell you what's down there. It doesn't
Hmm.
tell you how much of it there is. It doesn't tell you that you've got something really big that's not, just a little more dense than rock, or something that's smaller and it's a lot denser than rock. It just
Hmm.
tells you that you have a difference between this theory that the earth is entirely rock and that the earth is like something else. And I think that that's what this experiment at Fermilab might be pointing the way towards. We know there is something else if it's correct, but
Hmm.
it's not definitively pointing the way towards what that something else is.
But did we always know there was always something else? I mean,
Right. So,
I mean,
well,
we know
right.
there's
So,
got to be something else.
right. So there are some theories that, really do need something else to fix them, like dark matter, right? We
Hmm.
know that there's something that's causing the galaxies to rotate faster than, you would predict if it was just matter. So we know that there's something like that. But in terms of like some of these other theories, like supersymmetry and stuff, some of the arguments are made on aesthetic reasons, and it's not clear that that has to hold. The Higgs was the last thing that I'm aware of that was like, we
Right.
need something at this mass. And if it's not the Higgs, it's got to be something like it. But this experiment, from this result from Fermilab, comes out at a time where there are other hints of things that are just like not
Hmm.
quite agreeing with one another. And the language that the scientists use is that experiments and theory are in tension with one another.
Hmm.
That it's not, we can't say that they definitively disagree, but there is a tension in whether or not they do agree. And there's a few things floating around here and there that, if you're optimistic, you can say like, oh, this is definitively something new, but we don't really know.
Right. Now, I also, when I was reading up on this, there was this idea of when the results become like significant, when they're like
Right.
accepted that something is, and there was like, it's a 1, a 2, a 3, or a 4. And when you get
Right.
to the 4, it means you found it, you've done it.
Right. This
And
is 4 sigma.
right. And
Right.
that's what they were saying, like, well, once you get to the fourth, then you know. And I had never come across that before, and so I found that interesting.
Yeah, I've heard I think it might be apocryphal, right? So this is the idea of 1 sigma, 2 sigma, 3 sigma, and it's related to the idea of standard. These sigmas represent standard deviation if things
Hmm.
were a normal distribution or a Gaussian distribution. And this might be apocryphal, but I heard that the language that the journals would use, if you saw something at a 3 sigma level, you had evidence for.
Hmm.
And if it was at the 4 sigma level, you could say observation of, and if it was at the 5 sigma, it was like discovery. It was something like that. I forget what it was, but I think like the very first thing is like 3 sigma. Okay, you've got evidence for this. And yeah, 4 sigma is when people really start being like, whoa, because there's quite a few 3 sigma things that have come and gone.
Hmm.
We have so many measurements made all the time that you would expect some of them to be this. But yeah, 4 sigma is like, this is like, an observation of, or it's been seen. And then 5 sigma is like, for the Higgs, when it was 5 sigma, they were like, yeah, we've seen it, we've got it.
Okay, so it was just weird. I'd never. It was mentioned in some articles I read on this in particular
Yeah,
to kind of get. I guess it was to give the reader some way to gauge how
yeah,
like the level of certainty
yep.
around the discovery.
Yeah, it's like right now it's at 4.2 sigma. However, this recent lattice calculation makes it much less. I think it's like 2 sigma. And then the question is like, is the lattice theory calculation correct? There's going to be a lot of work done over the next year to try to really resolve some of these differences between the theory and the experiment. And the two theory, multiple theories are being used to try to calculate, or sorry, let me rephrase that. Multiple calculational approaches are being used to calculate this this quantity.
Right. It's because certain calculations have assumptions that other ones don't. So you.
Yeah, that's right. That's right. So you can do this calculation and you can say, there's always things that you don't know. And some of those you can say, well, I will take them from data. And in the data, this measurement that they made is really, 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 really close to what I need to put into my theory. And then the question is, well, is it close enough? And then other people say, forget about data. I can calculate this from first principles. But the way you program a computer to calculate it from first principles has a certain number of assumptions built into it as well. And so once you're getting down to, like we started off this conversation, this level of precision, maybe some of those assumptions are going to come back and bite you. And we don't know. We don't know.
Well, that's the fun part. We don't know.
That's exactly right.
If we
That's right.
knew it, why would we bother doing it?
That's right. That's exactly right. That's right.
So I want to talk about a little bit about, like, you've already talked about some of your research already.
Mm-hmm.
Is there anything you're excited about that some of your students are kind of getting into?
Yeah. So there's a few things that we've got going on. I'm really excited for this summer. Some of the things we're going to do. So there's one student that's going to be working with me. She's going to be helping me prepare for this workshop that we're going to run. Teaching theorists to look for new look for whatever theories they want to check. And to do this, she's going to be going through the instructions that we've put together, these guides for the workshop. And in doing so, she's going to wind up learning how to analyze the data herself. And I have a few really, really like speculative ideas, like for that I would like her to check. Once she's able to like analyze the data, she will be able to add numbers and square them and take the square root. Like really, really speculative stuff. So I'm excited about that. And then the other thing, so Scott, you and I met when you came to Siena to build cloud chambers
Yep.
back in the day. And that's been like a great project for students to work on. So these are cloud chambers that do not need dry ice. They use Peltier thermocoolers, and you stick it onto a cooling fan from a computer, and you can like see radioactive traces left by radioactive samples or cosmic rays. And we
I
started
still use mine every year.
It still blows me away
It
that you
still
can
works.
like turn it on and it works.
And it works. It's great.
but it's the size of a petri dish is the viewing area.
Yeah.
And so last summer I had a student start working on how we might scale it up, still using the Peltiers, but use a water cooling system to suck the heat away. And if we're able to do that, we might be able to get 2 or even like a 2x2 grid of Peltiers next to one another. And now you've got a much larger viewing area. You might be able to see more cosmic rays. We did not get it going we did not get it working last year, but we learned a lot. And so I've got a group of students that's going to try to work on it this summer. Because that project it fascinates me. Like I love the fact that, I don't have to go and get dry ice. I can turn it on. I can put a little sample in there. I see something.
Right.
And then the other, sorry, go ahead.
It's a great way to demonstrate that there are things that you can't see.
Yes.
And they exist.
Yes.
Because otherwise I could say there's cosmic rays and kids are like, sure.
Right.
I believe you. It's like, no, okay. When you actually see it and you can kind of identify it, and it takes you directly from this, we're kind of not doing science to like, wow, this is like real stuff,
Yes.
You can actually see
the invisible. It is making the invisible visible. Those cosmic rays are around us all the time, whether or not the cloud chamber's there. And then you put the cloud chamber there, you're like, oh my gosh, I've revealed something about the universe.
Yep.
And then the other thing that we've got going on that I'm excited about is we're running a workshop this summer for middle school and high school teachers to teach them about a board game that we developed at Siena for, again, middle school, high school kids, although the college kids are having fun playing it too. It's called Quantum Party. It's a board game designed to teach people about quantum mechanics. And I'd worked with a student about a year and a half ago to start trying to suss out the rules. And we went through a bunch of iterations that did not work. And then she graduated, and I worked with some other students to try out different things. And then over the last just under a year, I've been working with a faculty member in our creative arts department and a student who's doing a creative arts minor to do the graphic design for the game. We found a company in Wisconsin that you upload all of your graphics to. And like, we now have like a real like boxed game called Quantum Party. And there's cats. And because of course, quantum mechanics, of course, there's got to be cats. And we put together a pamphlet that kind of explains the game and the science behind the game, because the game is driven by like classic quantum mechanics related physics experiments. And we claim that there's an educational benefit for kind of like immersing yourself for half an hour in this game, where you've got to kind of like, you've got to hear some of the quantum terminology. So I think you could play the game and never really like learn the science and just follow what the cards say. But I think it's more interesting if you learn the science. And so we are hoping that the workshop, helps us develop a dialogue with teachers where we can learn, is this useful in physics or chemistry classrooms? How can it be more useful? And then maybe to collect ideas for like an expansion pack for like more quantum physics experiments in the game. We've got dice that explain about black body radiation and the double slit experiment. And I don't know, it's been a blast developing. It's actually kind of fun to play, at least if you're a nerd like I am. But it's been very cool. So I'm excited for that this summer also.
So some basic questions about the game.
Yes.
How long is a playthrough?
So there are 4 experiments. My wife and I played it, and we were able to go through like all 4 experiments in about 30 or 40 minutes.
Oh, really? Okay.
You can choose to go through, that was just with 2 people. You can choose to go through one experiment, and it takes like about like 10 minutes. The goal of the game with these cute little cats that you have is that the cats, you come into your lab one day and there's all these quantum cats that are running around. And they are having a party, and they're collecting party hats, and they're doing this by like running quantum mechanics experiments because they're just having fun in your lab. And so with my wife and I, we played it pretty quick because I lost every round and she quickly collected all 4 hats. But you can choose to just like do one of the experiments as a learning goal. And it can be like 10 or 10 minutes or so to get from one end of the lab bench to the other. That's how it works.
Okay.
The board is a bunch of lab benches that you've got to get across.
And I like that as a teacher because you can scale it up or down as far as time, because it's always important. Well, sometimes you get a game and it'll take you 45 minutes to play through it, and you're like, well, maybe I have enough time, but I still have to teach them how to play it.
Right. And so this is a large part of why we're running the workshop, because let me be completely honest, I am really ignorant of what happens in a high school or middle school classroom. Like, I have my experiences from 30, 40 years ago. But you guys are faced with a time constraint that I just cannot intuitively understand. And so my hope is that, it's really the teachers that are going to participate in the workshop that will determine, is this useful? Is this a game that kids, they check out for the night and they play it with their families and then they bring it back the next day and explain it? Is it something that kids are just going to buy on their own? Maybe it can't be used in the classroom. Maybe it's for like an after school science club.
Right.
I really don't know. I've enjoyed not just designing it, but playing it, but I do not know if or how it can be worked into a regular curriculum. And that's for you guys or whoever shows up at the workshop to kind of tell us.
I always think that you won't know if something's broken until you get middle schoolers to try it, and then you'll see if it's broken or not.
There you go.
And if not, they will break it. They'll find some way.
That's right. My 7-year-old son, we played it a while, and we didn't do the whole game, but we had fun. And he just, he likes rolling dice, and he likes flicking the spinner and moving stuff. And if there's a bunch of like elementary or middle school kids that come out knowing that like red light is less energetic than blue light, and they don't even need to be taught it when they get to school because they like learned it from the game. If they know that quantum mechanics is probabilistic because you've got these dice that you have to roll, that's like all that I feel like is a benefit. If like they just pick up some of these like ideas that, we usually teach them kind of in a more straightforward pedagogical basis. We've got these dice that we will use for the double slit experiment. And you have to like add them constructively if they're the same color. You subtract them from one another for destructive interference if they're different colors that they come up.
That's
my
interesting.
Goal, right? My hope is that the game makes it easier for people like you and me to teach then more formally, because students have been able to like, kids coming up through this have already developed a bit of an intuition through the gameplay. This is the hope, but we got to run the experiment to find out.
Uncle Bill says, cool. And
nice,
I agree.
Very cool.
I mean,
cool.
I use games in class. I run a gaming club.
Nice.
Right. So
very cool.
And there are some science games I've tried with them that have kind of fallen flat, and there are some that they pick up on immediately, and they love. Usually they like the ones where they can beat me.
That's always a plus if you can beat the teacher,
right? So like so that's always a bonus for them. I'm always the first one out usually if it's that type of game.
This game is really, I tried to like invest some sort of like strategy in it, and I just could not make it work. And at the end, I'm just like, it's basically like Monopoly, Game of Life. It's kind of like random driven, but you're having fun. You're moving cats around. You're collecting party hats. What's not to like after that,
Yep. But a lot of the problems with games is, and this is the problem I had with the game Pandemic. I don't know if you ever heard of that. It's a popular board game.
I've heard of it. Yeah, I've heard of it.
And it's used a lot in teaching. But there's a lot of onboarding that goes on with that game.
Right.
It is very involved. It's a very good game, but it's very involved to get kids going on it. And so those kids that might lose you, you'll lose them. right?
Yeah, 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 yeah.
Whereas that's why I like the idea of it. You can play a game in 10 minutes because then
Yeah.
I can introduce it for 10 minutes. You can play it for 10 minutes, and then you can have 10 minutes of kind of like,
Talking.
talking about it or having any kind of discussion, like you were saying, is good. Whether it's
Yeah, yeah,
like, did you like that one? You want to do the next one? Or, uh,
yeah.
it doesn't necessarily, I think a lot of teachers think that it has to be about the content when you
Right,
talk about a game. It's more important to have any kind of reflection at all.
right, right,
You
right.
know,
Yeah. So
did
we've
you
got.
like it? What did you not like about it? I
Yeah,
mean,
yeah, yeah.
because even if you're thinking about liking it or not liking it, you think, uh, Uncle Bill says, game link is broken, 404 error. So,
Is it the Game Crafter Games Quantum Party?
yes.
Is that the one? Yeah.
Yeah.
So that one. So I didn't know that he would get a 404 error. That's where the game's going to be able to be sold. We're making some final tweaks to the graphics once we got the first one. So it should actually be available for sale there in the next 2 to 3 weeks. And it might just not
Okay.
be live now because we still have the shop site shut down because we're making these edits to the graphics.
Okay.
But it should be up and running in the next 2 weeks or so.
Yeah. Yeah. If you go to just to gamecrafter.com/games, you get to their site and you can see
You'll be
all
able
the
to
games
search
that they
for.
have in there. Yeah. And you can
Yeah,
search
yeah,
for
it's
it
an
later.
interesting site. I only just, learned about it from the student like a year ago. And this idea about onboarding and stuff like, if I say the word cones of Dunshire, do you know what I'm referring to?
I do not. Maybe Uncle Bill does. I don't know. But
Cones of Dunshire is a reference from a TV show called Parks and Rec, and there was a
okay.
character who he designed a board game that was like, it was a kind of a spin on it was like a reference to Settlers of Catan, but it was so complicated and so Byzantine that nobody liked it until he like introduced it to a bunch of other accountants. And the first versions of this game were that too. And I kept referencing it. I'm like, is this two cones of Dunshire? And this is like, yeah, this is too complicated. And so it really,
Mm-hmm.
really got scaled back
Right.
to something like I feel is pretty basic. But again, we'll find out.
Hey, well, like you said, you can, if you want more, if you decide to add the expansion packs or something
Exactly.
like that,
Yeah.
there you go. And that's marketing right there too.
Yeah, no, that's right. That's right. That's right. And I learned a lot. How do you explain these fairly complicated, concepts to like a middle schooler?
Mm-hmm.
The idea of Rutherford scattering, which discovered the nucleus, or the black body radiation, which
Mm-hmm.
tells us about quantized energy levels, or and stuff like that. It's yeah, and it's all in the game, and there's some little like fun things on the cards, like, oh no, you've encountered a quantum barrier, roll to see if you tunnel through. You don't need to know what those words are, but
Right.
it's in the pamphlet, it explains it if kids want to learn more. And then again, then they get to like your class or my class down the road, and they're like, I already know this. I played this game, I know about the uncertainty principle, and
Yeah.
because your cat might have to move back a few squares.
Well, then we get into the sad state of physics education, which
Mm,
which I probably don't need to tell you about. But I feel
that's
a lot
another
of pressure
conversation.
myself. I teach, for eighth grade, at least at 1 year in middle school, you get half a year of chem, half a year of physics, right?
Right, right,
For the
right.
vast majority of students, that half year of physics is all they get in their entire life.
I
Uh,
know. I know.
and whereas most kids will go on and do chemistry, but they won't go on and do physics,
Right,
um, which
right.
is usually the case because even though it's not true, that physics is seen as more math heavy,
Yes.
whereas I think chem can be just as math heavy as the physics.
Yeah. Depending on how deep you want to
Yeah,
go into
and
it. Yeah.
it's also unfortunate the way physics is taught in New York State is very
Yeah.
much like an algebra class or a
It's
trig
regimented.
class
Yeah.
versus discovery and scientific thinking.
Yes.
Yes. And that's just
Yes.
my take. I mean, we probably agree on that.
I think we do.
If you ever look at a physics regents, you're kind of like, they don't have to know anything. They just have to shove numbers into equations and then get an answer out the end and put it down.
Yes. And we when we get a lot of students, in a first year, depending on who's teaching what course, we might have to spend a lot of time of breaking them of that habit of just like, well, this is just like, if I plug the numbers in the right place, I should be fine. It doesn't matter how I think about it. And for some students, this can be really difficult for them because they have been incentivized. They're like, if I approach physics in this really algorithmic way of like plugging in numbers here and getting something out, it gets them an A. And then there are some courses they take when they get to college and this approach does not work. And they're like, wait, why am I getting a C or a B? This used to be A work. And so there's a bit of a disconnect in what's expected, once they get to some of these classes in college. And it takes quite a bit of social engineering and discussion with the students about like, okay, we are now have a different level of expectation than, not just your teacher in high school, but the regents, like you said, the teachers are under a real mandate to like inject a certain approach or certain facts. And then we're like, well, we're asking you to kind of like make a deeper connection. And that can be a struggle for, a number of the students just because that was not what they were expecting.
Yeah. And I will freely admit, even after taking 2 years of physics in college, it wasn't until I taught about like Newton's 3 laws of motion that I really finally understood it. And I was like,
Me too.
I get it now. I'm like,
Yeah,
why did it take me having to teach it for like several years? Because like you would try to teach it and you would see inconsistencies in your own thinking, and what you were reading, and you're at a point where like, it's not necessarily that you were, sometimes I was wrong, but other times when you're just like, I was just, I had a misconception about how this works.
Yep.
And it's just, I don't know. I don't know how to fix that other than having everyone teach physics for a year.
I know, right? Wouldn't that be the dream and stuff? Wouldn't that be the dream?
I know, but that was, none of it was mathematical. It was all just what will happen to something in certain phenomena. Why do these phenomena, happen? How do we explain it? It's that level thing, which we're trying to do in K-12 education now, with phenomena-driven education.
Yeah, I feel like we do not, and we struggle with this at Siena. We have so much content we want to cover. I feel like we do not give the students enough time to just think about it and mull it over. Like you said, you discovered these inconsistencies in your way of thinking because you had to teach it, and you were forced to find time to think about how you would explain it to your students. And even if our students are not going to have to teach it, I feel like they don't have time to just like turn it over in their head and look at it from a different angle, because we're throwing so much homework at them, and a new concept is the next week, and that there's not enough time to just sit and think about the implications of what they've learned. And that would be my dream, is to just find a way to give more students time. Not all of them would take the time. Like if I said, hey, I'm going to teach you half the material and I just want you to think about it more deeply, they would not do that. They would just do half the material and they would think about the same level. But there would be some students that would, I feel like, really relish the time to just like I said, turn it over in their head a few times rather than just focusing on like the next homework assignment.
Yep. And I think it's simple thought experiments. At least for me, it's like, all right, if you were to play baseball, in space,
right? Yep.
How long of a game would it be?
Oh, nice.
Or if you played catch, how could you throw the ball back and forth more than once?
Right. Yep. Yeah. Exactly. Yeah. I remember.
And you could just debate it. You could just, and eventually someone's going to bust out the whiteboard and the marker, and you're going to like try to figure it out mathematically, probably, because that's what you do in physics.
Right. So I remember, in 8th grade sitting in like Spanish class, like bored and watching the clock and watching like the second hand go around, the minute hand. And I remember thinking, how long would that hand have to be so that the tip of the hand was moving at the speed of light? And the teacher was working with some other people. And so I just like sat down and I was like, well, it's got to go around in 1 minute. So it's got to travel this distance. And I knew like the circumference, right? And the reason why I was like messing around with that was because I was bored. And I feel there's a real benefit to having time where you're bored because it forces you to start thinking about how do you play baseball in outer space and how long, right? And there is something about, and look, I am on my phone a lot. I am on the computer. I am checking Twitter. But there is something I feel about a lot of kids nowadays that they never allow themselves to be bored. And it's that boredom where you start thinking about like, ugh, I got nothing to think about. Maybe I'll think about physics from class today. And then you start to think about it and you play it back in your head and you're like, wait, did that make sense or not? And I don't know if this generation is going to have those opportunities for boredom, which is where I think creativity often comes from, and forcing yourself to think about stuff and make connections that you wouldn't have otherwise. I feel like they constantly want to be like stimulated. They want to be told what the answers are rather than just having, again, that freedom to like think about it and what could it be? How do you play soccer on the moon or something like that? Yeah.
Right. And I think a lot of it is also the dialogue that you would have with students and students have between themselves. That's the
Yeah,
ancient,
yeah, yeah.
the Socratic type thing where,
Right.
the actual talking through it, either with
Yeah.
yourself in your own head, as you were
Yeah.
talking about, or, with someone else, because trust me,
Yes.
8th graders can argue. All right. Pretty much anyone at every age can argue really well. All right.
Right, right, right. Oh, I'm
But certain people
sure.
like love to argue, and that's a good thing,
Yeah,
right?
yeah,
That
yeah,
should
yeah.
be encouraged if you have a productive argument,
Yeah.
for sure.
Yeah, yeah, yeah,
Um,
yeah, totally.
and another thing that I noticed in education in COVID times
Hmm.
is, you know, that inability to do the hands-on physics labs.
Yes.
Um, there's a certain
Yes.
level of critical thinking and problem solving that comes with hands-on, messiness.
Yes.
Versus like if I do an online lab, I'll take pictures of, the results essentially, and they just look at it.
Right.
But they don't have to set up the apparatus.
Right.
They don't
Right.
have to, figure out, if they're rolling a baseball down a ramp, think about, well, where should we start it from?
Right. That's right. That's right.
Or what do I
Yeah,
do
yeah,
when it hits the edge? Do I count that one or not? Or
right, right. Does it matter if I started at different points? Does that
right,
affect, my measurements?
right.
Like
And
yeah.
and you're limited by what the simulation gives you as far as variables.
Right.
You
That's
know,
right. That's right.
versus kids just like to play, and I usually allow for a degree of play because that's the whole point of this. Sometimes it's just to
Yeah,
play
yeah, yeah.
around and see what happens, but in a simulation you're limited in your variables. So like you can adjust the height and you can adjust the mass, that's it. you
Right.
know
That's not the
Eh,
real world.
right. Real world, you
Uh,
can change the angle of a ramp, you can do all kinds of other
it could
crazy stuff.
the ramp could be slippery, you
Mm-hmm.
could polish the ramp to get it to roll. Yeah, we started revamping our labs about 4 years ago, and the last 2 years it's now propagated through I think our first year program where we have these much more inquiry based labs where it's much less hand holding, much less, just following procedure, and it's more like measure the acceleration due to gravity. Here's your equipment.
Mm-hmm.
And the equipment is not set up for them, because we found that they would not think about like, does this need to be level? And it's like, yes, it needs to be level. But they would be like, well, when I came into the lab, it wasn't set up as level, so I thought it should be set up for me. And so we really try to set it up so that they have to think through all the different aspects of their experiment. But again, they're not used to it. And so there's a bit of social engineering that has to take place where we're like, this struggle is part of the learning process. If I tell you what to do, it's not going to stick with you. You have to play with it some to try to get in there. Like, I just want to get out of here. I just want to like do my lab and be done and leave early. But like, no. You got to struggle a bit.
Yeah, and that's one of the
bored.
things I noticed that my kids were like, I did the first like hands-on lab a couple weeks ago with some kids because we're finally in person with a group of enough kids to actually do something. And usually at this point, we would have gone through an entire school year up to April of them having to figure things out for themselves because I have to teach them like what you said. And at that point, they get the idea of, all right, I know what I have to look for. I know the expectations of how a lab or an experiment should be set up. We've gone over, independent and dependent variables and, confounding variables and everything. But I hadn't done that. So you get to the first one and it's just, confusing.
Yes. Yeah.
Because everything builds.
It's a big shift. It's a big shift for them.
And I worry about kids that decide, if God forbid that's a choice to keep learning remotely, you're never going to get that experience.
That's right.
Which helps your brain think about experiments and variables and
That's right.
setting things up. So,
yep. Because eventually, no matter what, eventually they'll have jobs. Usually, unless they're video game designers, they're going to have to interact in the real world. They're going to have to get used to like real equipment and real equipment that is imperfect. And how do you get the most out of that imperfect equipment? Which is a good, rule for life anyways. How do you make the most of an imperfect situation?
Well, I think even with a video game designer, if you're working on a physics engine.
Yes, absolutely.
Right? Especially, modern games, you want some of that messiness in there as far as what other variables might affect how this wave looks in the water. Right? So, I mean, it and if you haven't had experience working with extraneous variables, you wouldn't know. Now, before you go, because I know you're getting tired, you got stuff to do.
Oh, sorry, but I didn't mean. I apologize for that. But yeah,
that's okay.
I was up late last night. I didn't mean that was not. That was not trying to be like
this boring conversation. Oh my God, no.
No, that wasn't it. Sorry.
This we're gonna play a game, and since we spent a lot of time talking about the donuts of physics, meaning accelerators, because they're shaped like donuts. I'm going to ask you 3 questions about donuts.
All right, sounds good.
We'll see if you can get at least 2 or 3 of those questions correct tonight. All right.
I'm scared. Okay.
All right, so I'll see what you know about donuts.
Okay.
All right. Question number 1.
I'm ready for it.
All right.
Give it to me, Scott.
Adolf Levitt, a Russian-born immigrant, invented the first automated donut machine in 1920. What did he call it? Was it A, the Glazer of Might? Was it B, the wonderful, almost human automatic donut machine? Or C, the best darn donut maker in the world?
I'm going to go with B.
It is B. It is B.
It sounds like something almost vaudevillian. And that sounds about the same time period. Oh my gosh, I did not know that. That is fascinating. We have a running joke in our house. I see that you just drank out of a donut there. My wife, because my wife, so my wife's a physics professor, so we make these really nerdy jokes. A donut is topologically the same as a coffee cup because you can stretch a donut into the same shape. They both have one hole, right? So your cup right there has a hole in it. Anyways, it's right. So you could topologically deform that into a donut. Anyways, it's a bad joke, but we
topology,
yeah.
I get it. I had read that somewhere else before as well.
All right. So, number 2. I'm ready for number 2.
Question number 2.
Okay.
Now, people love delicious baked goods. I'm one of them. I'm dreaming about one tomorrow morning, maybe. Which of the following statistics is true?
Uh-oh.
This is about the people being named for donuts. 10 people in the United States have the last name Donut, spelled Doughnut, or donut.
Okay.
Or is it B, 5 people have the last name Sprinkles, or C, 253 people have the last name Bearclaw.
Oh my gosh. So you said one of those is true?
One of those is true.
So 10 people have the last name Donut, 5 people have the last name Sprinkles, or 253 people have the last name Bearclaw?
Yep.
I'm gonna go with C. 253 people have the last name Bearclaw.
The correct one was A. 10 people have the last name Donut or Donut. There are 12 people that have the last name Bearclaw.
All right. So I was just off by an order of magnitude.
498 people have the name Sprinkles.
No. Oh my gosh.
This was based on the white pages. Like if you go to white pages, like you just search in names. This was,
oh my gosh.
From a,
All right,
from
I'm
a while
learning
ago.
something.
So
I'm learning it. All right, I'm trying to get 2 out of 3.
that many
so the
people
pressure's not
named Sprinkles though, kills me.
Oh my gosh. Oh my gosh. That's all. I had no idea, but I will keep that knowledge with me now for the rest of my life.
Right. So the next time you go to name a
Next
pet
time I meet
or
somebody. Yeah. Next
they have
time I
like,
meet somebody named Sprinkles.
my name is Sprinkles Bearclaw.
All right, I got to get the last one. All
right, question 3.
I'm 1 for 1. I'm 1 for 1.
Question 3. Now, donuts are not known for being healthy. In fact, they are known for being unhealthy. Which of these stories about donuts and health is actually true, actually happened? Is it A, that a donut will make you gain 5 pounds if you have one a day for 10 days? Is it B, because of the affinity of the dough in a donut for fat, that 10% of a donut is actual fat? Or is it C, that to go from a size 6 to a 14, to portray Bridget Jones, Renee Zellweger actually ate 20 donuts a day for 3 months?
Oh wow. Okay. The first one was that if you ate a donut, so I'm assuming that the idea is if you ate a donut more than you usually do per day, right? Not just one donut.
Just one donut a day.
Right, then you would lose like so much weight. So what if you ate?
No, I mean you
donut,
ate your regular food.
Yeah, no, I know
your 2,000 calorie diet, but you added one donut to it.
Right, and you did that for how many weeks? 2 weeks?
For 10 days.
For 10 days, would you gain 5 pounds? I feel like I would. I feel like that could easily be a fluctuation for me. That's like 200 pounds. The second one was like 10% fat. Oh my gosh. Because I keep thinking about a glazed donut, but that's different than the dough.
Remember, a glaze is a sugar. It's not a fat.
Yeah. Good point. And then Renee Zellweger. Like I remember, I liked Bridget Jones's Diary actually. I'm not ashamed to admit it. But did she eat 20? She couldn't have eaten 20 donuts a day. So if I ate an extra, oh my gosh, I know I'm overthinking this. I'm terrible at these things. My wife would be so good at, because she's much better with like understanding food than I am. I feel like they could all be right. No, but the fat, wait, so what's the fat in a donut? There's like, is there eggs? There's eggs in the batter. There's a bit of fat.
Well, you fry donuts.
Flowers.
That's where you get the fat from.
That's right.
You got to fry it in the fat. The delicious fat.
It's so good, right? It's so good. It's delicious. That's right. Oh my gosh. Can I say all of them are right? No, I have to pick one of them.
You got to pick
two
one.
Two of these are not true?
They're not true. I just changed the numbers, honestly.
Yeah, gotcha. God, I know I could
Hey,
put on 5.
support church, what's going on?
I'm gonna go. I'm gonna go with A is true that you could put on 5 pounds, but maybe I'm just projecting. But I'm gonna go with A.
You would only actually gain 1 pound
I feel like I would
in
gain
10
5.
days, not
Okay,
5. I feel
fair.
like I would gain 5 too, but
Yeah,
that's
right.
the
But
statistics that I read.
so
Uh,
which is it?
C, that she ate 20 donuts a day
Good
to
for
go from a
her.
6 to a 14
That's
in just
commitment
3
to your.
months.
That's commitment to your craft.
Yep, it
Wait,
is
so what was
commitment to your
so
craft.
how much of a donut is the fat then? You said
25%.
no.
Yes. That's what I read.
No, that's amazing.
It's
No wonder
amazingly delicious. That's what that
no
is.
wonder they're so good. Now I'm gonna go to Dunkin' Donuts tomorrow. Um,
Uh,
that's fantastic. My wife will be disappointed in me because like she's Canadian and that's the land of Tim Hortons donuts and stuff,
oh,
which
okay.
is part of the Canadian
Well,
landscape.
some of the first donuts were made in America in New York, supposedly.
Really?
So the first instance of a donut mentioned in literature was in New York. So we can bank on that because it was a donut. It was Dutch, of course, the
Oh,
donut.
interesting.
So
Interesting.
as everything originally in New York was Dutch, essentially. So
Right. Oh, fantastic. Oh my gosh, now I really want a donut for tomorrow. I'm gonna go to Dunkin' Donuts and
yeah,
get something.
yeah. So now that
Those were
even though
good
you know
questions.
that it's 25% fat, you're still gonna potentially
Like you
25%.
said, it's
I'll have to go do
tasty,
some
tasty
actual
fat.
research. Yeah, so I
That's
guess
right. That's
in Washington Irving was first to use the word donut in 1809
really
in his History of New York.
1809. So
Balls
was
of
it just
yes, balls of sweetened dough fried in hog's fat and called donuts.
because they're like dough and they like little walnuts or something like that? Huh.
Yeah.
So
So,
I'm hoping that the pandemic allows for people to travel next year. The AAPT winter meeting, so that's the American Association of Physics Teachers. I haven't been to one of their meetings in probably about 5 years or so, but I'm going to try to go in January if we can travel. It's in New Orleans,
ooh,
and I've never been, and I'm very excited to gain like 15 pounds while I'm down there,
you will.
including what is it the beignets,
Yeah, oh yeah, the beignets.
which is like something donutty or something.
Yes, it's
Like
basically it's like fried dough,
I'm
essentially.
excited.
Yeah,
I'm
it's
gonna
good.
go have I'm gonna go have that every morning for breakfast if I get down there.
Yep. Have your beignet for breakfast, and then your jambalaya or
Right, gumbo for
gumbo
lunch,
for lunch,
crawdads for dinner and stuff.
crawdads for dinner, and
Yeah.
your po' boy if you want that.
I
So
will
it is a
muffaletta.
culinary wonderland down there in Louisiana.
This is what I hear. I'm very excited. I'm hoping, knock on wood. And I think if the way I would go is like I'm going to try to give a talk about the quantum party and what we've
Yeah.
learned at the workshop this summer. Anyways, if I get down there, I will have some donuts and I will some beignets, and I'll remember this conversation. And I will ignore the fact that you said that they're like 25% fat,
Yeah,
and I
just
will
ignore
just
that.
I'll walk a lot down there. I'll try to walk off the calories.
Uncle Bill Druin asks, wonder if Bruce Yeaney goes to that. Yany.
Oh, I know that. I know that Bruce Yeaney's YouTube channel. That guy's fantastic. Yeah, Bruce Yeaney's got I think he was in the Midwest somewhere. Who is this? Uncle Bob is one of the you said is this
Uncle
the
Bill Druin.
Uncle Bill? Sorry. Yeah, Bruce Yeaney's channel is fantastic. I think he retired from teaching about a year ago, but I think that is exactly up his alley. It's middle school, high school, college, university, physics professors, lab instructors, physics teachers, um, companies that sell equipment. People give talks. There's demos of lab equipment there. I gave a talk once on the cloud chambers. Yeah, it's a really cool meeting. I went to one in Sacramento, and it was very inspiring just seeing what people are working on. There was a couple of great talks about physics labs, to what you were talking about, doing more
Hmm.
hands-on stuff. So yeah, so I'm excited to go. I find it a very inspiring meeting.
Yeah. Plus 10 nerd points, I guess, for you.
Plus what?
Plus 10 nerd points.
There you go.
You got,
Exactly.
yeah,
That's
you
right.
got more geek cred, according to Uncle Bill Druin.
Nice. Yeah. Yeah.
I don't
Nice.
know if you
Nice.
needed more. It was pretty geeky tonight.
I
It's quite good.
I do my best. I bring the geek. I bring the geek hard and stuff.
Especially now that you have your own game. I mean, that's like full on
I,
geek cred right there.
and
You
again,
publish your own game.
I just want to emphasize, if I didn't emphasize enough, how many students like really worked on this. And like Abby
Yep.
Huffman, the student who worked on the graphic design, she's a multimedia graphic design student. And I gave ideas and suggestions, but she really like came up with this design, which I feel it's like I would not have come up with this. Like I would have come up with
Right.
something like very like serious and steampunk and dark colors. And she's like, no, check out, this is like so much more appealing. I feel like
Cats. Yep.
Cats and the colors and the coral and like yeah, no,
Definitely.
she did amazing.
Awesome. Yep. You got to take her with you when you give your talk. When you go to
she and one other student, I think if all goes well, she'll give a talk about the idea of graphic design for scientific explanations, or a poster. And then there's another student that is going to work with me this summer. We're going to explore doing animations of like math explanations. So I don't know if you know the YouTube channel 3 Blue 1 Brown. The animations that he makes to explain these high-level math concepts, that's a Python library that he wrote, and it's available to anybody. And so I've started to explore how you can use this to do not like really high-end math explanations, but like kind of reinforce basic algebra or basic physics 1 ideas, basic kinematics. And we've done some, very simple proof of principle stuff. So there's one student, she wants to be a physics teacher, actually. She's in our education certification program.
Nice.
And we're going to try to come up with like, maybe just like a half dozen, like 30-second, like explanatory snippet videos and stuff using this animation library that the guy wrote for his channel.
Awesome. Yeah, I just looked up the 3 Blue 1 Brown.
It's
amazing. I
amazing.
actually haven't seen. I'm not a math person per se. Like I don't teach it, so.
Yeah. No.
But
I go to it because I'm not a math person either, and I need to like understand it sometimes.
Yeah.
And he's got these great videos explaining stuff.
Awesome. Yeah, I'll have to check that out. Share it with some of my students.
It's amazing. It's really cool.
Awesome. Very good.
Cool.
Well, I think we're good.
Awesome.
And
Scott, thanks so much for inviting me on. This is
thanks for coming in.
Talking to you about all these.
I'll have you in again the next time I come across some physics supposed discovery that I need explained to me.
I am here. And look, if you ever, when things are better and easier, if you're ever looking for like a warm body to come and like, talk to your class about like any of this stuff, feel free to call on me. I'd always love to talk to the next generation of students and stuff.
Oh, if we play the game in class, I'll definitely invite you in.
Oh my gosh, that would be awesome. So do you think you'll be able to make the one of the 2 days for the workshop? Do you think you're going to be able to make it?
I should be able to. We're finalizing like summer schedules, like my daughter's work schedule is getting finalized and things like that. So that's all happening pretty quick now here in April and May.
Understood. And look, if you can't make it, totally understand. The game will still be available for purchase. You can get your school to chip in for it. And then I'm happy to give you even like a side private tutorial about the gameplay and stuff.
Now, I do want to go to this a lot because there is the possibility that it's in person.
I know, right?
Which would be the first like in person like teacher science thing that I've done in a year and a half, 2 years. So
fingers crossed.
Fingers crossed. The rates go down.
We are planning on in person, and if things change, that's great. But as of right now, I've been given the go ahead to have whatever our number is, 16 or so student or teachers, so participants. So
Yep.
fingers crossed, fingers crossed.
Yep. That's the goal. So I'm excited about that.
Yeah,
If nothing else, a
no
chance
doubt,
to
no
go
doubt.
someplace that's close and not in my house
I know.
and not at my school either.
I'm with you. I'm with you. I know. I know.
So hopefully, if anybody else watches this, that's a teacher, middle school to high school, definitely, check it out. Even if you're out of state, right, Matt? They can come in
Absolutely.
from,
No, absolutely.
Massachusetts, Connecticut, Vermont.
Yeah.
If you're in the area, even, Ohio, wherever, you can make it.
Yeah, we're working with our school to give CTLE certification credit. So it'll be 7 hours of CTLE credit. I have no idea how that transfers across state boundaries, but I would think it would be fine. I mean, I don't know how those things work, but they will receive some sort of a certificate from Siena that this counts for professional development. It'll come from our education department at Siena.
So usually if it comes from a school of higher ed, it's usually golden.
Nice.
For most districts. CTLE having that designation is, important for New York State in particular.
Yeah. Nice.
So to get, especially younger teachers, meaning not old like me, but where you have to get those CTLE credits. I don't need them. But
well, that's good. That's good. Well, it'll still be a fun time.
But this will be great.
Talk with your colleagues from across wherever, however many we can get to come.
Oh, I can't wait. I had so much fun when I went there last time for the Physics on the Frontier for that.
Oh, yeah. That was a good time.
Yeah, that was awesome. So lots of fun.
Nice.
So thank you so much for being here, and have a wonderful night. You can sign up, and I'll end this, and I'll be streaming again on Friday. I'll be playing some more Subnautica. So if anyone wants to play Subnautica or watch me play, that's what we'll do. So thank you, Matt.
Thanks,
and everyone else. Good night.
Good night, dude.